Good morning, everyone. Today, first we go through the first tutorial I put in the video, just for anybody who probably has missed it or was not present in the last weeks. So this is the Moodle page for this module, and here just remind you that all the lecture notes are here, and after each session, for example, lecture 1, term 1 was 2 weeks ago, an introduction. The recording of the session is here. You can watch it offline again if you wish. Lecture number 2 is for the last week, and the recording is just below. Okay? Every week, this is for today. Every week when we have a lecture, the recording will go behind the okay. So it is there if you wish to review the course that week. It gradually will be filled. And also, there is a tutorial and exercise section here. For example, last week, I put one tutorial number 1. If you open it, it's an example, and it's for you to deal with and try to solve it. After a few days, I just put the solution here. This is the solution. I will go through it today now very quickly. And just again remind you that this doesn't have anything to do with your marking. This is just an exercise every week, just to have an opportunity to these different topics during the semester. So it is one of the best ways to learn this course. This is for you really to use. If you use it, I believe you will get skills for this module. If you don't use it, you will miss out. And as you have noticed probably, I also put one example here. This is a video for using EPABS. It's a software for analyzing different structures, as I mentioned in the previous weeks. And this is just kickoff for starting using the EPABS. And you need to go to the labs to use this software. It is on the machine in the Nelson labs. So you can go there and open this one and try to repeat what I've done and do whatever you want to do. I will keep posting such videos during the semester, and we will have such some sessions in the lab, but it is not for now, it's for the second term. So we cannot wait until then. We need to start using this. And one of the uses is that in the coursework, you will need to really calculate something, some analytical solution, and also use the EPABS and show that these match. So it means that you verify your calculation based on some manual calculation, and you get sure that the EPABS software is doing well. And this is what I've done in this example for a very simple one. And we'll go through different examples during the semester for more complicated examples. And this is also some file that today probably I will need to talk about it, but because it's an example, I just put it in the tutorial section. But today, when we go through the lecture notes, we will at some point we'll get back to this file and I will tell you what it is. Is this clear? Okay, any questions? So this is the Moodle page really for you, and all the material are there. So just go there and have a look and try to do some of it, okay? So before I start the lecture, I just go through the solution. I'll put it here for you. This is the example until here, the definition of the example. So these are two beams, two cantilever beams, one here and one here, A, B1 and C, B2. The difference of these points, B1 and B2, is 5 millimeters. So when you put P here as an external force and you start to increase P, the B1 will deflect, gets down, 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 down until it reaches to the B2 point. Okay? Before it reaches to the B2 point, nothing happens for the right cantilever beam. It doesn't have any forces on it. But when B1 reaches to the B2, and if you start to increase P, they both together start going down, and they act as a unique structure together, right? So I want to find P when B1 reaches B2. The coincidence that these two reach together, where they do reach to each other. So the solution for the first one, for the A part, the solution is that we have had this in our previous slide, didn't we? For a cantilever beam with integration method, we calculated the deflection of the end of a cantilever beam based on concentrated load P. Do you remember? So the solution is PL3 over 3EI. P is external force, L is length of the beam, EI, are constants of the material and section. So if this delta would be 5 millimeter, B1 will reach to B2, right? If B1 comes down for 5 millimeter, B1 will be almost reached to the B2. So if you put 5 millimeter for the delta, which means 5 over 1,000, because I want to use meter as dimension, PL is 2L and 3EI. So the P would be 15 EI over 8,000 L3. This is the value of external force, which makes B1 down to the B2 point, right? Until P reaches to this level of force, nothing happens for the B2. B2C, this beam is just a straightforward, no force, no deflection. So this point, B1 reaches to the B2, and if you press P more, they go down together, so both of them will deflect. They will work as a unique structure. So the second part of the problem aims to find the difference of B1 and B2 point when P is more than the case of A. So it means that if P is more than this value, which makes these two beams work together, what happens to the deflection of the B point? Because B is B, there is no difference between B1 and B2. They are together. They are 1 point. So the solution can be like this. This is the B1 or B2 point, and they are working together. So if I cut an epsilon in the right side and epsilon in the left side, these are the shear forces where I cut. There are here, you can put the axial force, you can put the internal moment. It doesn't mean that they are not existing because I didn't put them here. They are there. I didn't put them here because I don't want to use those equations of equilibrium that use axial force or internal moment. I just want to use sigma of forces along y direction equal to 0, this one. And for summation of F over y direction equal to 0, I only need the forces along the y direction, which are these P1 as shear forces here, P2 shear force, internal shear forces here, and the external force P here. So here, this is epsilon, this is epsilon. Here in this part, in this cutted section, I want to write summation F along y direction equal to 0. So I come up with P1 plus P2 should be equal to P, this one, right? Any question here? So B1 has come down for a certain amount of deflection, right? When B1 comes down for a certain amount of deflection, if you write this formula for the left structure, see, B1 has get down for 5 millimeter plus another delta because it gets more down, okay? But B2 has got just a delta down, not those 5 millimeters, right? When, for example, when B1 and B2 are here, down here, B1 is delta plus 5 millimeter, B2 is only delta, right? So I just put 5 millimeter plus delta for this formulation for the left beam. B1 see P1 is the force for the left beam. So P is divided to P1 and P2. P1 works for the left beam, P2 works for the right beam. P1, 2L, 3I, and this is the implementation of this formula for the right beam. For the right beam, I just put delta, not delta plus 5 millimeter, because it's for B2 point. This is for B1 point. So delta is P2L3 over 3I. This is the formula for the right beam because the force is P2. This is the formula for the left beam because the beam is P1, the left beam. And these three equations what are the unknowns and what are the knowns? Because you have P1 and P2 as unknowns, really. And you need to, for example, for these three, you need to calculate P1, P2, and delta. Okay? You have three equations and you have three unknowns, P1, P2, and delta. You can calculate all of these three. If you do that, for example, you can just substitute delta from this equation to this one, then you can get something between P1 and P2. So you can substitute P1 against P2 from this to this, and you get one of these, and again, use the other equations to get the rest. Right? So you can calculate P1 and P2 versus P. P is the external force, and EIL, you know them, and also the delta. So this delta is the deflection of B2, which means how much B2 gets down, but the deflection of B1 is this delta plus 5 millimeter, right? Any question?
Sorry, P1 equals P divided by 9 or?
9, yes.
Okay.
Yeah, that's 9.
So the 9, I didn't.
You mean this one?
Yeah, where did 9?
P over 9, yes.
And where did it come from?
From the solution of these three together. I didn't write the details, but for example, put the delta from here, substitute the delta from here, okay? You will get something between P1 and P2, okay? For example, write P1 equal to P minus P2. Substitute P1 from here to this one, and you will get P2. When you get P2, substitute to here P2, and you will get P1. And when you get P1 and P2, you can put P2 here, you will get delta. These are three equations, three unknowns. You should be able to solve it. You have this in many other modules or mathematics. Is it completely new to solve three equations with three unknown parameters? It shouldn't be. So, how many really took a look at this example before today? Good, one. You're in a good position. I'm pretty sure everybody knows how to solve it and didn't need to go there and just take a look. Okay. Good. So I just wanted to emphasize that these are for you. These are for you to exercise every week, almost every week. I don't put them every week, maybe twice a week or maybe every week. This is the best way to learn this module. Otherwise, you can try other ways. But as far as I know, this is the best way to learn this module, by practicing small amount of efforts each week. Otherwise, this is not really a module to be learned overnight. You need exercise. You need pen and piece of paper every week. Spend a couple of hours to think about the problems, and they will settle in your mind, and you will get familiar with the concepts. Otherwise, if you try to learn these things over a few days, you will be mixed up with many stuff, many things, and you will get many problems probably. So the best way is to practice every week. And this is here for you to be used. And you will see the results when you go for the exam. If you trust me, if you do these exercises during the semester, when you go to the exam, you will totally feel that what you see in the exam is familiar to your eyes. Otherwise, if you don't do these practices, when you go to the exam, you will think that the questions are written in Chinese language, not English. And you're not familiar with these stuff. What does it mean? What is this? What is that? So, or any other languages that you don't know. I mean, Chinese language. I don't know Chinese language, but it's totally new for me. So, if you put something in front of me, I don't understand. So, if you try to exercise these things, you will certainly be more comfortable during the exam, right? Okay, let's go back to the slides. Any question? Okay. Today, we're talking about a method which is called finite difference method. And to give you a heads up, sometimes we are lucky enough to have this opportunity to be able to check our calculations. For example, for these classical examples that we reviewed these weeks, there are some analytical solutions. For example, for cantilever beam, for concentrated load, the deflection of the end of the beam is known as PL3 over 3EI. So this is analytical solution like this example. We know what is the deflection. And there are some, this is analytical solution, but there are some numerical solutions as well. Because numerical solutions are important, because when the structure gets complicated, gets very big, you cannot really work with analytical solution. You cannot use this method when you want to analyze a very big structure. So what you should do, you should really use other methods, including numerical solutions. And numerical solutions need to be verified in some ways. It is good if we would be able to verify our results based on some analytical solution. For example, today we are going to learn a numerical method to analyze a beam like we did in last week's and today, and verify the solution. We have an analytical solution, we have a numerical solution, compare them and see how they work. Are they close enough? If they are close enough, we say, okay, these methods are working well. And our benchmark is the analytical solution. The analytical solution is the right one, is the correct one. And the numerical solution should provide us with some answers close enough to the analytical solution, if they are working well. If they are differ too much, there is a problem. And that's why we are going to discover today how the numerical solutions work. One of the well-known numerical solutions is called finite difference method. And another one is finite element method, which is another module for some of the master students. And I'm not sure if bachelor was going to get an optional module. I'm not going to check, but There is a module. Exactly after this module, I go to another class without any gap between. There is a module finite element method. This is a little bit older than finite element. Both are somehow the numerical methods, aim to solve a problem like a cantilever beam or whatever you want to do. So today we want to see how this finite difference method works, and we work with some real example to see how the results are close enough to the analytical solution. Don't scare about these formulas. You will see at the end of today that using them is quite straightforward and very simple to do. Assume that we have a function y versus x. This is the function y versus x. And there are some points. The function of y versus x is represented by some points, not a formula. Okay? You can have 100 numbers versus another 100 numbers. One would be y, one would be x. So you can plot y versus x, but point by point. Okay? You will get these points. The y versus x are these points. You don't have a formula, a closed form formula. You have some points. This is always the case in reality, because when you want to, for example, measure wind speed, you need to put some instruments, and the instruments work like that. It measures the wind speed every, let's say, 10 minutes, and save it on some, I don't know, computer or hard disk. And you will have, for example, if you leave it for a year or two, you will have a couple of 100,000 data. All of them are discrete. They are called discrete data, not continuous data. So they have points in this time versus time, actually. For example, the wind speed is this one in this time, that one in that time, goes on, goes on, goes on. For the earthquake load is the same. There are some instruments installed in some places, and they have some connection to the electricity, so they have some batteries. So they are there. If an earthquake happens, they save the movement of ground very precisely in every 0.005 seconds. Means 5/1000 seconds. 5 milliseconds. They are very precise instruments that are able to record the ground motion for every 5 milliseconds. And the earthquake usually lasts in 1 minute, less than 30 seconds, let's say 1 minute. In 1 minute, which means 60 seconds, in each 5 millisecond, it has a data. So you can plot the different data together. You will come up with a figure with a shape of the function of ground motion versus time. So these are real applications of different functions that work with discrete data. So get back to the finite difference method. The derivation of dy over dx at node n is here at this point. What is the derivation of the function? This is the definition of the derivation of the function, the limitation of yxn plus delta x. Delta x is this one. I've shown it with h. This is delta x, okay? Means y at xn plus dx. This is This is this yn plus 1. Just for simplicity, I named it yn plus 1, which means the next data. I would call it the next data, I would call it the previous data, okay? This is the point that we are going to write the derivation. This is the next data minus the data at my point divided by the delta x. This is the definition of the derivation. When the delta x is very, very, very small, like an epsilon. So it is the derivation of the next point minus the current point over delta x. If delta, I will call the delta x as a h, I put approximation here instead of equality, because really here I'm working with some real numbers for h, like an earthquake case is 5 milliseconds, for example. But in mathematics, delta x is not 5 millimeter, it's epsilon, which epsilon goes to 0. Okay, approaches to 0. But in reality, when I want to work with real numbers, I need to assume something for the delta x, a small one, but still I need to work with some numbers. So I just put here, it is an approximation. And that's why, because I put some real small numbers for delta x, that's why these kind of approaches are approximate. They are not precise mathematical approach. They are numerical. All of the numerical approaches are approximate approaches, but still enough precision. So this is called forward difference because I'm judging about this derivation based on the next point. This is my point, the current point, and I'm using the next data to judge about the derivation of function y, right? I can somehow work with the previous data to come up with the derivation of y over x, and that works like yn. See, this is yn plus 1 minus current, next one minus current one. This is current one minus previous one over delta x. This means that I'm judging about the derivation based on the previous data and the current data. I just come back to this slide again after this. This can make difference when the function changes rapidly, like exactly wind speed or earthquake ground motion. Assume that the red function, this red one, is the real function. That in reality we have it, but we need to measure it in some points because of the limitation of instruments. So it's a wind speed or whatever. And it changes rapidly in this point. Okay, this is my current point. This is the next point I've measured, and this is the previous I've measured. I don't have anything between. I have this data, and this data. If I judge between my current point and the next point, the derivation would be the angle of this line, right? If I judge about the derivation based on my current point and the previous point, the derivation would be the angle of this line. And you can see the angle of these two lines are totally different. And they should be, because this is a point somehow the red function is moving down instead of up. It's changing the direction. It's a sharp point for the function. For the sharp points of the function, this is really a problem. So it is important. And which one is right? I don't know. None of them is right somehow, because really here, or maybe a little bit here, the derivation is 0 because it's changing to down. So for the left side, the derivation is positive. It goes to 0 and gets negative. Yeah. So to be honest, the forward difference and the backward difference, both of them are somehow not very good. Not wrong, but not very good. But we can define a new concept which is called central difference, somehow averaging between these two. And if you, for example, if you average the angle of this line and angle of this line, you will come up with this blue one, which is more or less more realistic. Better estimate of the real derivation of the red curve. So maybe the best way of representing the derivation is central difference, which is kind of average between the forward and the backward. I just got back to the previous slide, which we have forward and backward and central. Central difference tries to use both of the points, the forward and backward, to have some average between them. So it says you can define the derivation of a function at something like the next point minus the previous point, but divided by 2 delta x or 2h. Means I'm averaging over this range, not over only this one or only this one, over whole this 2h range. This is a better estimation for a numerical case. So it is the difference of the next point minus the function at the next point minus function of the previous point divided by 2h. This is called the central difference. And we can prove that, okay, this one, we can define this part as a delta, and these 3 lines are nothing, just to show that this is an average between the forward and backward. So if we just add these 2 together, we will come up with some averaging, which is this one, the central difference method. So these are 3 different pillars that the finite difference method can work generally on. But usually, many of the finite difference methods work with central difference because the central difference is more realistic, and it can estimate the actual derivation of a function, a numerical function, very better precisely when the function has some sharpness like this one. So if we have the derivation, for example, we take this one for the further elaboration. If we have the derivation, this is the first derivation of a function. We can come up with second derivation of a function or third or fourth derivation of a function. Why do we need them? Because, for example, I need this one because the integration method for the beam are like d2y over dx2 equals to m over ei. The last 2 weeks we spoke about this, didn't we? So we need this one at least. These are good for something else as well. But for example, for the second derivation of the function y, we can say, okay, this is the first derivation between the next and the current. This is the first derivation between the current and the previous one. And we come up with this one. This has the next point, the current point, and the previous one over h2. Just take this into consideration. We don't need the rest. I want to use this one instead of this one to solve a problem. Remember that, again, see, I'm borrowing this one for here, because I know that d2y over dx2 is m over ei. This is, we spoke a lot previous week. If somebody has missed it, just please go there and watch the offline record. And what I'm going today is to replace this part, d2 over dx2, by this numerical interpretation of central difference based on the finite difference method. So I'm going to say this is equal to m over ei, right? Okay. Assume that we have a simple beam. This is x-axis, this is y-axis, and this is y function I'm looking for. I'm looking for the deflection. And this is an arbitrary loading on the beam, whatever. Okay? For the next slide, I will go for a real example. I'm just showing you what does it mean. You can divide your beam into a certain number of points. For example, here I divided the beam to 5 points. 1, 2, 3, 4, 5, right? And equally distributed points. So if it's L, you will have, when you have 5 points, you will have 4 segments. 5 minus 1 segments. 1, 2, 3, 4. So each segment is L over 4. 25% of the total L, isn't it? So, and this is the curve of moment, internal moment over the beam. But assume that this is just schematic shown of the internal moment. This is an arbitrary shape. This is not exactly the value. So this is the arbitrary shape of the external loading. This is an arbitrary shape, just schematics shown that this is M1, M2, M3, M4, M5. I know M1 is 0, M5 is 0 because we have two simple supports there. So the internal forces should be 0 at this point and this point, right? We have 5 points, so see node 1, node 2, node 3, 4, 5. What can we say in each node? In node 1, we can say y1 is 0. Why? Why would we say that? It's a support. Absolutely. It's a support and y1 is 0. M1 is 0, y1 is 0 because it's a support. Simple. In node 2, which n is 2, I'm going to use this one. Put n equal to 2. What I will get? Here, if n is equal to 2, it would be y1, like this, minus 2y2 plus y3 equal to h2. This is h2. H is this segment length, L over 5, L over 4. Okay. You remember h is delta x. Okay. This is L over 4. So this is h. This is delta x. Powered by 2 times m over ei. M2 over ei. Right? And I know y1 is 0. So I will get some equation between y2 and y3. Right? Let's repeat it for node 3. I'm just putting n3 in this equation. If I put n3, I will get y2, 3 minus 1. y2, this is coming from here when I put n equal to 3. y2 minus 2y3 plus y4 equal to AH2 times m over ei. M is m3 because I'm writing for node 3. I've got a new equation between y2, y3, and y4, right? Repeat it for node 4. You will get y3, y4, y5. Again, you are using m4. And at the last point, m5 is 0 and y5 is 0 because it's a support. At the end and beginning, y are 0. At the between, you have these three equations. How many unknowns you have in these equations? Obviously, y1 to y5 should be unknowns, but I know y1 is 0, y5 is 0, so the unknowns would be y2, 3, 4, right? 3 unknowns. Are these known or unknown, M2, M3, and 4? No. Known or no? Which one? Known? Yes, known, because it's a simple beam. We can write equilibrium equations. We can just draw the internal moments, what we have done in these weeks. Because this is a determinate structure, beam. It's not indeterminate. You can simply use the equilibrium equation to write, to figure out how the internal moment varies, and you can just make a section wherever you want versus x, and you can draw the actual internal moment, right? So when you have the M2, M3, M4, you have 3 unknowns, y2, 3, 4. You should, oh, the solution was here, I didn't realize. When you have 3 unknowns and you have 3 equations, so you should be able to solve them, shouldn't you? That's easy. I cannot proceed because this is a schematic example. I don't have the values. I just go for a real example and just try to implement these concepts, okay? But just to recap, this is analytical solution. When I try to solve this one, I integrate 2 times over the equation, as I did in last week, right? I integrate this one. When I integrate it, this is exact analytical solution. But when I replace this one by this central approximation of the derivation, second derivation, and I try to use this one approximately equal to m over ei, this is finite difference. This is approximation. So you can, at the end, you can compare the approximation with the exact solution, right? And for the approximation, you need to divide your beam into some points, some segments, and really depends on you how many you want to divide, how many segments you want to make for your beam. And we will try, for example, for different n to see which n is appropriate. And then I'm trying to write this equation equal to m over ei for different n values, n over equal to 1, 2, 3, 4, 5, 6, 7, 8, whatever you have. When you write this for n times, you will get n equations. Some of them are known because of the boundary conditions of the supports. The rest would be easy to be solved, right? And if you solve by 2, 3, 4, it means that you have some points of the y function. So if you have y1, 2, 3, 4, 5, you can draw the y function with 5 points. Obviously, if you have been divided before the n equal to 10 or 20, you would have 20 points to draw your function, right? The more points you get at the first place, the more precision you will have when you draw the final y function, right? So I'm going to practice this in a cantilever beam, again, because you have the analytical solution of the cantilever beam, and we'll see what happens. But before we start, I want to tell you that, first of all, The analytical solution for this beam is this one. This is coming from the integration method, right? If you integrate over the d2y over dx2 equal to m over ei, 2 times integration, you will come up with this when you apply the boundary conditions of the support. This is only one fixed support here. So this is the exact solution, the right solution. So whatever you come up with the numerical solution should be compared with this one, right? If you put x equal to L, you will come up with minus P L3 over 3EI, which I used for the previous exam tutorial. So today I want to solve this problem with the finite difference, but for 3 cases. To be honest, I cannot choose n less than 3, can I? Less than 3 is 2. I cannot divide this element into 2 parts. It means that the whole beam would be 1 segment. That's not rational. So I start with 3. 3 is probably perhaps the minimum value for f you can imagine. So I will try whatever this is for n equal to 5 and 8. Just some arbitrary assumptions. And let's do this, and I will increase n to see what happens. Okay? If you understand what we do for n equal to 3, it's easy to repeat it for the other cases, n equal to 5 or 8, or even further. So let's say what happens for n equal to 3. First of all, this is a determinate structure, determinate beam, and you can draw the internal moment here. And for this one, because this is a fixed support here, you don't really need to calculate the support reactions in this example, because you can really make a section here and take the right cutted section of the structure, x is from here to here, and the internal moment would be px. It's a linear distribution of internal moment, and you can draw px from 0 to L. Here would be 0, here would be minus pl. So really it is not difficult to calculate internal moment versus x, right? This is the internal moment versus x for a determinate structure, and I'm going to use this for my example. And because I have divided my beam for 3 nodes, which means I will get 2 segments, whatever n is 3, you will get 3 minus 1 segments. If it's 5, you will get 4 segments. If it's 8, you will get 7 segments, right? So for the n equal to 3, this is exactly this graph, m over x, for 2 segments. For 2 segments, here it's minus pl, here is minus pl over 2, here is 0. When I write the formulation, I will need to use the different values of m, right? See the previous one? I need different values of m. I need these m2, m3, m4. So that's why I'm dividing the internal moment in different segments that I'm assuming. So when n is equal to 5, I will get 4 segments, each L4, L over 4 is the length of each segment. So this is minus PL, this is minus 3 PL over 4, 2 PL over 4, 1 PL over 4, right? Here, if n is equal to 8, you will get 1, 2, 3, 4, 5, 6, 7 segments. So when you get 7 segments, start 0, 1 PL over 7, 2 PL over 7, 3, 4, 5, 6, 7 PL over 7. Because it's linear. because it's linear, it goes one by one, right?
Why is the second one and which equals to 5?
Second one means this one?
Yeah. Or is it supposed to be?
This?
Yeah.
This is not 3, this is 2.
Ah.
PL over 2, which means 2 over 4, right? 1 over 4, 2 over 4, 3 over 4. This is 2 over 4 or 1 over 2, okay? So is it clear, this is slide? So I'm going to use this formula for n equal to 3 and use these data, these 3 data for the n different n's for n equal to 3, right? So for node 1, I would say y1 is 0, theta 1 is 0. And if theta 1 is 0, which means that the first derivation of y is 0, and the first derivation of y is y2 minus y1 over the segment lengths, which means y2 is 0. Don't worry about it. I will discuss about it why this got 0. And if I put n equal to 2, I would say the second derivation of y over x is this one. This is exactly this one, right? And this is equal to minus PL over 2EI. Minus PL over 2EI is this one. I'm writing for n equal to 2. I'm writing for this one. And you should put n equal to 2. So it would be y1 minus 2y2 plus y3 equal to m times h2 or delta x2, right? L2, this is L2 powered by 2 is L2 over 4, right? If you put y1 and y2 0, you will come up with y3. What I've done really is that I've used the formula for only 0.1 and only 0.2. I cannot use it for 0.3 because if I use it for 0.3, there will be some terms indicating about y4, and I don't have any y4. I only have y1, 2, 3. I cannot really implement this equation for n equal to 3 because this term will be y4. So for the last point, I cannot do anything. I only can use for the n equal to 1 and 2, right? But still it's okay because when I implement for the first one, because really in the first place in this n equal to 1, I have a fixed support which gives me 2 conditions. First of all, y1 is 0, and second of all, theta 1 is 0. So really, when I work for the first node, I will get 2 of my unknowns. y1 is 0, and theta 1 is 0. Theta 1 is the first derivation, which when I apply it, I get y2 is 0, right? But this is a solution with a very high level of approximation because it says that y1 is 0, y2 is 0, but y3 is something, which means that the deflection is 0, 0, 0 until here. Okay, it goes down like this. It is somehow wrong because your n is very unrealistic. So n equal to 3 is not a good choice. And what you get for the last point for y3 is minus PL3 over 8 EI. And you know the exact solution. You know the right solution. What it is? It is minus PL3 over today we talked about. Tutorial, what was it in tutorial?
3.
3, yeah. Or if you put L, x equal to L, you will get here minus PL3 over 3EI. It was here, it was in the tutorial, and it was in the last week. Please, 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 please review what we teach every week and take a look at the teaching material and the tutorials. Otherwise, you will be missed after a few weeks. So, and here we get minus PL3 over 8 EI. It's quite far away from the exact solution. It's not a good estimation of the exact solution, is it? So the problem is that because we are talking about n equal to 3, it's not a good choice. That's why we increase n by 5. And we are going to use this curve. We are going to write the formula for 4 points, 1, 2, 3, 4. Still, and again, I cannot write it for n equal to 5 because I will come up with y6, and it's not something that is defined in my problem. So for n equal to 5, I need to write it for node 1, 2, 3, 4. Again, for node 1, y1 is 0 because it's a support. Also, theta 1 is 0, and it results in y2 is 0. So always y1 and y2 will be 0 because of the first line. And it means that whatever n you get for your solution, y1 and y2 will be 0. And it means that if the n would be as much high as you get a very small difference between y1 and y2, it would be fine. But if it's too large, the approximation would be high. So the n should be some high numbers that y1 and y2 would be close enough together. Still, they are not here. 5 is not enough large number for the n. So y1 and y2 are 0. We go to node 2. So again, I write the formula, and this is coming from the internal moment. And I have y1, y2, y3. For the next point, I have y2, y3, y4. I have y3, y4, y5. Right? When I increase y by 1, it's like just increase these in indices by 1. 1, 2, 3, 2, 3, 4, 3, 4, 5. Right? The right part comes from really the this curve. For the first point, you use this one. For the second point, you use this one. For the third point, you use this one. For the fourth point, you use this one. Right? Still, you have 3 equations, and you really have y3, 4, 5 as unknowns, right? So just, and it is not interactive. You know y1 and y2 are 0, so put just y1 and y2 0. You will get y3 straightforward from this equation. Put y3 here. You know y2 is 0. You will get y4 straightforward from this equation. And you know y4 and y3 from the above. You will get y5 from this equation straightforward. This is not like substitute from this one to that one and get complicated. It's very straightforward. So you will get y3, 4, and 5, right? If you if you draw the deflection for n equal to 5, it would be 0, 0, 0, still 0 here. Okay, it would get something, 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 gets to here. Okay? What is the Y5 deflection? It's minus 14 over 64. Or let's say what is in the denominator? It's 64 over 14. What is 64 over 14? It is 4.5, 4.57. The exact solution is 3. 3 should be in the denominator. With the assumption of n3, we got 8. Exact is 3. The right answer is 3. We got 8. When we increased n by 5, 8 became 4.5. It means that we are approaching to the right solution, to the 3. It's a good way. It didn't increase, it decreased. So the correct solution is 3, should be in the denominator. It was 8, now it's 4.5. Let's see what it is when we get n equal to 8. N equal to 8, again, you should just repeat the same steps as before and nothing more. You're just using n equal to 8. So you're writing the formula for node 1, again, y1 is 0 because of the support, theta 1 is 0 because of the support, and theta 1 is 0 leads you to y2 is 0, and you will write the formula for node 2 to node 7. You don't write it for node 8 because you will come up with y9, which you don't have. So really you have from node 2 to node 7, you have 6 unknowns, which are really you have 7 equations and 7 unknowns. You have really 7 unknowns because y1 to y7 are unknowns. Okay? You have 2, 4, 5, 6 equations and 1 here, right? So, for example, for node 2, this is exactly the same. y1, 2, 3, 2, 3, 4, 3, 4, 5, 4, 5, 6, 5, 6, 7, 6, 7, 8. And the denominator is delta x2 or LH2, which in this case, when n is equal to 8, each segment is L over 7, right? Because you have 7 segments. Okay, so it's L over 7 powered by 2. And where do these come from? The right side of the equation. These, they are internal moments, right? PL7, 2 over 7, and so on. So this is for node 2, node 3, node 4. Let's go to node 10, right? And these equations will result in y3, 4, 5, 6, 7, 8. Right? And you have y1 to y8 in which you can draw the deformed shape. Still, y1 and y2 are 0, and the rest goes to y8. So y8 is what is in the denominator? 340, what is it? 3 over 91. What it would be?
3.8.
Yeah, 3.76 or 8. So it's getting better, right? It was 8 in the denominator. The correct answer is 3. It got 4 point something. Now it gets 3 point something. It is approaching to 3, which is the correct answer. When I increase n. If you increase n larger, or larger amount of numbers, you will get better results compared to the analytical solution. And don't forget that we are lucky here to have analytical solution. It's not always the case. In complicated structures, we don't have analytical solution. We're just trying to test if our method does work in a good manner for a simple structure. We have analytical solution. Otherwise, always we don't have this situation. Another thing is that if you look at the process that I'm following here, it seems that from each equation that I go forward to the next equation, there are some algorithms, known algorithms, like you know, it's a beautiful algorithm that is repeating, like whatever you have in the denominator here, y1, 2, 3, just increase by 1. It means that y1 gets y2, y2 gets y3, y3 gets y4. But the coefficients here are constant. This is 1 minus 2 plus 1, 1 minus 2 plus 1, right? In the denominator is the segment lengths powered by 2 squared. So what is the segment lengths? It is the total lengths divided by n minus 1, which means that when you have n equal to 8, you have 7 segments, right? So somehow it's beautiful. And in the right side, you have the internal moment in that point. So this is the internal moment in point in node 2. This is the internal moment in node 3, node 4, node 5, node 6, node 7. Look, it means that you need to, because you know the internal moment is minus PL in the left side, right? You know it's minus PL in the left side. So because you're using for example in n equal to 2, you know this is you need to divide the minus PL over the number of segments, which is 7, right? And just use one segment when you go one step forward. It is minus 7 PL over 7. This is minus 6 PL over 7, 5, 4, 3, 2, 1. This is a rhythm there, right? Whenever you see a known algorithm, repeated algorithm like this, there is a repeating algorithm between different equations. When I'm going from this to this, from this to this, it seems that you can define some rules to come up from this to the next one, right? Whenever you see this pattern, just remind that computers are designed to do repeated algorithms. And this is the best point that we go to the computers and ask them to do this for us. Because, for example, if I wish I know what would happen if the number of n, the n is equal to 100. So you need to do this 100 times. How do you feel if you want to do that? Somebody says, you don't look at the Moodle page any time. What do you expect to do 100 times of this? What? Machines are very good to do this kind of job. Even 100, 200, 300.
He's volunteer. I will do for 500 without any claim, right?
Don't bring a computer to the exam.
No. In the exam, you're trying to see if which one is better, you or a computer. If you do better than computer, you will get A+ or something like that. In the exam, I'm not expecting you to do 100 times for the N. I will expect to perform some performance that the computer cannot. The computer is good in repeating stuff, but still human being is better than computer in understanding the concept. If I want to illustrate the concept of, I don't know, integration method for the computer to integrate and do the boundary conditions, it's very difficult. It's really difficult to write an algorithm for the computer to solve different structures based on that integration method. It's really difficult because there are many conditions that you need to decide, especially when it is a determinate structure or indeterminate structure. But in such a problem that you need to repeat something, computers are very good to do that. And today, we are going to try how we can do that. And that's why I've put that Excel file in the Moodle for you. If you go to the tutorial, you will find this file, finite difference for a cantilever beam, right? If you open it, it's a Microsoft Excel file. Before, you see, I've tried it for N3, 5, 8, 10, 20, 50, and 100 already here. And it's very easy to regenerate it for n equal to 1,000, 10,000, whatever you want. Before I start to manipulate with this one, how many worked with Microsoft Excel or anything? Good, good. Okay, half of the class almost worked with Microsoft Excel. I just try to give you some hints for those who haven't worked so far with Excel, and also some extra hints for those who have already worked with Excel. Excel is a spreadsheet that assists you to do some really beautiful exercises if you want, with numbers, numerical stuff. And you can do really beautiful things if you learn how to use it. And you can use it for many other purposes, like time management, or I don't know, making a table for yourself for groceries, weekly groceries, or making, it's like a sheet. Remember, in old times, there were some paper sheets with some charts. Still, there are some. Some people are used to take some of them, stick it on the refrigerator and write we don't have yogurt today. Okay, tomorrow I will go to buy a yogurt. So this is a kind of matrix to use. And you can put, for example, different days of the week and different times of the day and come up with some sort of matrix to understand, okay, I am in this day and I'm in this time, so I need to do that task. So this is very useful when you want to organize yourself in a kind of matrix form, right? Good. So, for example, see how I use this. If you understand one of these sheets, which I will explain to you, you will understand the rest. The rest are just increasing n. And you can make another one for yourself. Just focus to understand the first one. This is node. Okay? Node 1, 2, 3, 4. I just made 50 nodes for myself, and here I'm just using these 3. I'm not using any more. But I just left these here just to be used in the next sheets. Right? But I can just remove these. Right? And when you want to make your nodes, if you start here, there are 2 ways to fill this column. You can write 2, 3, 4, 5, 6, 7, 8, 9, 10. Go to 50, it takes a little bit time, 10 minutes or 15. But the good feature of Excel is to just write 1 here and go to the next one. Okay, just go click here and say equal. See what I write here, you can see here. Okay, equal to, this is my mouse. Okay, just click here and you can see it is blinking like this. And press enter. See, if I go here, it is equal to B3. B3 is this one. B3 is this cell. Spreadsheet has some cells, right? The left numbering is 1, 2, 3, 4, 5. The right, the columns are A, B, C, D, E, F. So this one is B3. So B4 is a formula referring to B3 plus 1. Okay? If you write a formula like here, B3 plus 1, let me delete all of you until 50. Okay? We don't have here anything. I just write 1 here. I go to here and I say equal. You will see here, equal. Just press this one, or either don't press it. Say equal B3. I just typed B3. 1. Enter. It is not just 2. It is the previous one plus 1. And if you go, see this very small square here in the right side of the cell here, in the junction of here, okay? Here. When I go here, see my cursor? My cursor is a big plus. When I go here, it is kind of another plus, small plus. If you go here and double click on this point, not this point, this point, when this goes from this plus to this plus, okay? When I double click on this, it fills all this column based on this formula I typed here. Okay, for example, here it is B4 plus 1. This is B5 plus 1. This is B6 plus 1. Everything is the previous one plus 1. So it means that if you want to make 1,000 numbers, only you need to do the first one, write a formula for the next one, and just fill the rest. It's easy, right? So, because it was yellow, all the others got yellow. It gets all the attributes of the previous one as well. So this is the node. The analytical solution and the final difference solution. This is the analytical solution, this is the final difference solution. How? The analytical solution is X and Y. So the analytical solution, I know. For the analytical solution, I just used all the 50 points because to have a very smooth curve, Okay, that's why this curve is the analytical solution, right? With I use all the 50 points for the analytical solution just to be just to have a real correct analytical solution. So this is 0. The next one is the previous one plus 1 times by 50 minus 1. Why? How does it come from? I told you, if you have 50 points, you will have 50 minus 1 segments, 49 segments, right? You have 49 segments, and for this case, I'm inherently assuming that the length of the beam is unity, is 1. So in each of these, I'm adding 1 over 49 as a segment length to the previous one. So each segment length is 1 over 49. It goes to here, where for the n equal to 50, the last one, the length is 1. So I'm using L equal to 1 in this example, because really, what was the formula for the deflection of the last point? It was minus PL3 over 3EI, okay? To be honest, PL3 over EI is constant in all the solutions. And I'm only working with that 3 in the denominator. So I can just assume P is 1, L is 1, E is 1, L is 1, whatever is 1. I'm using only the coefficient. So if you come up with a solution, just put PL3 over EI and times everything with that. Okay, that's why I'm assuming L equal to 1. So what is Y? Why is this? Right? I got it from the analytical solution. Right? Px3 over 6EI. See? This is the first one. Px3, this is x, powered by 3, over 6 EI. Forget about EI. I didn't put E, I, and P. I inherently assumed P, E, I are 1. Okay? I'm somehow using x3 over 6 minus x2 over 2 minus x2 over 2. Okay? If you go for the whole, you will come up, and I just drew this blue line based on, if I click on this, you will see this is x and y. These two are plotted here. This is the exact solution, the correct solution. What is the benchmark? Your numerical solution should be close enough to this blue one, otherwise there is an approximation. So, for the, is it clear, this one? This is just coming from the analytical solution, and this is coming from the finite difference. For the finite difference, we have x, so this is different. Here n is 3, okay? X has only 3 points, n equal to 1, 2, 3. The first one is 0, the next one is the previous one plus, this is n, okay, minus 1. Why I put dollar here? This is a beautiful trick that you should know. When you say G1, okay, when you say G1, if I say G1 in this formula, G1 is this one, N, right? G1 is this one, 1 is here, represents N. If I use G1 in my formula here, and if I take it and bring it down, G2 will, here you will get G2, G3, G4, okay? But when I put $G, $1, it means that when you are getting down the formula, don't touch G1. G1 will be the same, stays G1 as G1. It doesn't change G1, 2, 3, 4, 5. See, for example here, when I say C3 plus something, when I come down, it's C4, C5, C6. I want to be C4, C5, C6 because I want to use different numbers when I'm instructing this one. But here, I don't want to change n because n should be constant in all the formula. When I want something to be constant during the formula, I put $, for both the column and row. $2. Each dollar, when each dollar comes before something, keeps that constant for when you repeat the formula and you just take this down. Okay? This is the internal moment. So the internal moment is -1. I'm really assuming P and L equal to 1. So it is here at the first point is -1. So the next one will be something like this. What is F3? F3 is the previous one. And I want to be constant. Times G1 N minus B4. B4 is this one, the node number, divided by N minus 1. For example, if it is really this formula, this one should go, the denominator should be n minus 1, and the numerator should be the denominator, what is the denominator? Because this 7 is really n minus 1. 8 minus 1 is 7. But this 6, how you can make a formula for this 6? This 6 is this number minus the number of this point number, the node number. 8 minus 2 is 6. 8 minus 3 is 5. For example, here, 5 minus 2 is 3. 5 minus 3 is 2. This is really 2 over 4. 5 minus 4 is 1. You can define the internal moment based on the n and the number of nodes. For the numerator and for the denominator, only n minus 1. Just play with it and you will figure it out. And why? Why? I'm just trying to write this formula, for example, this formula there. For the y, the first one is 0, the second one is 0. It's always the case. And the third one, you need to just follow this instruction. For example, any y is the internal moment multiplied by the delta x powered by 2 plus 2 times of the previous one plus 1 minus 1 time of the y 2 times ago. See, here I'm deriving y3. Y3 is this one times this one. Put these two in the other side of the equation. If this goes in this side, it would be plus 2y2. If this goes in that side, it would be minus y1. So y3 is this multiplication plus 2y2 minus 1y1. So this is exactly that formula. You need to go through it to understand. And if you draw this one versus this one, you come up with this figure. Obviously, it is a y function based on 3 points, only 3 points. So if you have only 3 points, you can imagine, you cannot really anticipate that this function with 3 points matches this real exact solution. There is a significant difference between the blue one and the orange one. And this is the approximation we're talking about. And this is really not an approximation, this is an error. This is really an error. The distance is too much different. So if I increase the n by 5, everything is similar. I just completed this based on 7 points. Okay? I just reconstructed this part. So with 7 points, it's getting better. Still, they are different. With 8 points, a little bit better. Not satisfactory. Still, 8 points has too much calculations to do, see? If you want to do this on the sheet of paper, it's a hassle, isn't it? So that's why we are going to use Excel. It's really easy to just go through Excel to do this. If you go for 10 points, I don't anticipate too much because 10 and 8 are almost the same. With 20, quite better. With 50, that's my guy. Good. Because they are almost the same. And 100, you cannot understand which one is blue, which one is orange. Right? And if you want to repeat it with for 200, you can either work with the same sheet, or you can simply right-click here and say move or copy, and it says create a copy. Okay, it creates an identical copy of this one. I just put it beside it just to remember. This is an identical copy of this one, and you can just rename it if you wish. Example, equal to 200, okay? And work in this new sheet if you want. It's better not to mix up everything together, okay? Keep the sheet that you are certainly sure that works good, and try to repeat the sheet for the other numbers. So do this at home. Try it for the 200 or whatever between these numbers for 30, 40, 60, 75 numbers to see what happens. And
Is that something that can come up in coursework?
yes, absolutely. But not the whole. This is a part of that.
Yeah. Perfect.
So see, it's not difficult. It's something that we go step by step, and I want to be sure that you get something from this module and you feel that, okay, I'm solving a real cantilever beam, and this is my solution, and this is converging to the exact solution. So I'm pretty sure that this works. And when you feel this sense, you can feel that, okay, I'm getting an engineer, to be an engineer. This means engineer. Otherwise, playing with numbers is easy for a child as well. You can play with numbers, whatever you want. But when you prove that, okay, this curve is showing the real deflection of this beam, and I have the analytical solution, I can prove my calculation is correct. So that's, in that case, you deserve to be called an engineer. Otherwise, playing with numbers is easy for everybody. Because I was shocked last semester, not last semester, last resit. There was a very simple beam, not cantilever, but not for yours, for the master students. And if the coursework was to just do something like this, but not with finite element, finite difference, with finite element, which should be quite easier than this one. And very few people could verify their calculations. And they got really some big errors like 2 meter difference between the deflection of their calculation and the software, and they try to justify it. Okay, this is a very good calculation, and this is what I got from the software, and this is my hand calculation. And my marking for that is 0. Because you're going to be an engineer. Otherwise, it doesn't make sense. You design a beam or whatever, you get 2 meter difference for the deflection and you justify it instead of going back and get your calculation and find your error. It's unacceptable for an engineer. Totally unacceptable. You should be able to justify your calculation. Okay, you can say here, you can say when n is 3, the approximation is as large as we can call it an error. But we know where this comes from. This comes from our assumption of n, and it is very low. 3 is not enough for n to be a good assumption for the final difference method. And you should increase it to get a better answer. And the last point is that, okay, we come up with different shapes, but I said this is relatively good and 50 is good, but intuitively, is there another solution to better make a adjustment, make a justification, which case is good for n? The last point deflection is minus PL3 over 3EI. Yes, now we all memorized it today, didn't we? So I want to just focus on this point because it has the maximum deflection, doesn't it? So it has the maximum deflection. I want to just draw the deflection of the end of the beam based on the approximation method and the analytical method versus different assumptions for the n. I just did it here. The x-axis is the number of nodes, n. Okay, and the data are here. This is 3 based on 3, 5, 8, 10, 20, 50, 100. This is not the case in my case. From 3 to 100. Okay. This is the solid line is constant, and it is really minus 1 over 3. 0.33333. Remember, P is L, P, L, E, I, everything is 1. You can say it is this one times that term, PL3EI. Okay, that's constant. This is what should be. This is the exact solution. This is the analytical solution for the end node, for the right node, the last node, right? And the hash curve is the same node deflection based on finite difference solution. When n is 3, it is here. When it's 8, when it's 10, 20, goes down. And you can justify for yourself which point and where should be enough and as an approximation for your study. If I look at this, I would say, okay, this is the exact solution. Somewhere here, the dash curve is almost approached to the exact solution, right? Somewhere here, but it's really depends on the designer choice. But you cannot obviously choose somewhere here because the changes are very significant in this region. Even 20 is not good. You should choose something probably more than 50. More than 50 here, we can call these two curves almost identical. Not identical, almost close enough together, right? So we can say, assuming n more than 50, let's say, is a good assumption for this problem. Otherwise, the finite difference method doesn't work with a good approximation level. Would you be able to repeat it at home for different n's? Yeah, it should be easy. Try to do that. It gives you some skills that helps you with different kind of problems in this module and other modules. This is finite difference method for civil engineers and for simple beams. And even you can try some other cases rather than the cantilever beam. You can try another beam if you like. If you don't like, I will force you in the coursework to do that. Good, that's it for today. Is there any question? All the class is dismissed, and have a good day.